Jai Hind viewers, we welcome you back to another episode of Expert Opinion from MRO Digest forums. A few days back, I came across this article which tells us that the center releases a draft roadmap for R&D for green hydrogen manufacturing and storage. And the Union Ministry of New and Renewable Energy has released this draft roadmap for the research and development. And as per the draft roadmap, the plan is to develop efficient, safe, and cost-effective hydrogen storage methods that enable high-density storage, reduce leakage, and allow for easy and quick refueling. Viewers, we have with us an expert, Brigadier YVR Vijay. He has spoken on this subject on our channel extensively, and there are videos which you can access from our YouTube channel. So I thought that it may be a good idea to take his expert opinion on this new development and hear from him what does he feel and how this will help the country. So Brigadier YVR Vijay served in the Corps of Electronics and Mechanical Engineers, where he was Chief Managing Director of an Army-based workshop. After retirement from the Army, he entered the renewable energy sector, where he was COO of Enercon India Limited and subsequently the COO of Suzlon Global Services Limited. He is now a subject matter consultant on renewable energy to Boston Consultancy Group, McKinsey, GLG, GuidePoint, Alpha Sites, and Third Bridge. So, Brigadier Vijay, as I mentioned, the government has announced a draft roadmap to develop efficient, cost-effective hydrogen storage methods so as to enable high-density storage, reduce leakage, and allow for quick and easy refueling. What are the main highlights of the roadmap? Brigadier Vijay, please.
Jai Hind, sir, and thank you. So basically, sir, this is a series of policy decisions taken by the government as a part of the National Hydrogen Mission. It was on Independence Day 2021 when the Prime Minister at Retd announced the National Hydrogen Mission. And he had said that it is the future of the world, and he announced the setting up of this mission. And his aim was that India becomes the new global hub of green hydrogen and also its largest exporter. And the government announced capex investment of 35,000 crores to 2030 towards India's goal on hydrogen. And specifically 19,700 crores was given to the National Green Hydrogen Mission. So they announced a lot of measures, and this is one more in that series. So this particular article says the Indian government has released a draft roadmap outlining plans for research and development in the field of green hydrogen, in manufacturing and storage of green hydrogen. The roadmap aims to leverage the R&D efforts to develop cost-effective and efficient technologies for green hydrogen production and storage. So basically, they're looking at in phase one, design and development of large-scale electrolyzer systems, including the stack and BOP. So we have to understand stack is basically the electrolyzer. BOP involves the balance of plant, that is the green power coming in. It involves the water coming in, the purification systems of the water, and the storage on the other side. That is BOP. And this article has proposed three main approaches for promoting, and under short term, mid term, and long term. So they call it mission mode, which is the short term up to 5 years impact horizon. Medium term is up to 8 years, 5 to 8 years. They call it the grand challenge projects. And beyond and up to 15 years, they call it blue sky projects. So in mission mode projects, they are talking of electrolyzers which will be developed, something on biomass gasification technology. In the midterm, they're talking of power to gas technologies, demonstration of biomass to hydrogen, development of integrated net carbon negative solutions. And in the long term, that is they call the blue sky, focus on establishing global IP, a competitive advantage for Indian industry, R&D for seawater electrolysis, photochemical water splitting, thermochemical water splitting, integration with nuclear technology for waste to hydrogen will be developed. This is basically what the article covered.
Thank you very much, Brig Vijay, for that. So, can you tell us what are the characteristics of hydrogen which make its storage challenging? Brig Vijay, please.
Yes, sure. The first thing we have to understand is while hydrogen is an excellent source of energy per kg, it is also the lightest element known to mankind. 1 kg of hydrogen at normal conditions occupies something like 11,000 liters of space. So hydrogen needs a great amount of compression and storage at high pressures. It is highly flammable. It has an invisible flame, and it can ignite, between 4% to 24% air. That's all it needs for ignition. So one has to have a lot of safety mechanisms to protect against hydrogen-based fires. You all heard of the famous Hindenburg balloon incident when the balloon was filled with hydrogen and sent up, and when it caught fire, everybody died in it. So safety is a big issue in hydrogen storage and transportation. Hydrogen has a very low boiling point, close to minus 253 centigrade, and a freezing point around minus 259. So a lot of energy is required to liquefy hydrogen also. But it is an excellent carrier of energy. It's got the highest energy content per kg. So that is why hydrogen is such a great fuel. It is colorless, it is odorless, so leakages are very difficult to identify in case of hydrogen. So we must take care on that. It is non-toxic, so that's a good point. But it reacts with metal, it forms hydride, so it's not such an easy element to store.
Thank you for that. So, you had mentioned that all storage of hydrogen demands compression because hydrogen, being the lightest gas, occupies huge volumes. What are the challenges and solutions in the field of hydrogen compression? Brigadier Vijay, please.
So hydrogen in natural state, kg of hydrogen occupies something like 11,000 liters of volume. And if we have to store it in either in steel vessels or plastic vessels at this pressure, you can imagine the capex involved in creating containers. And 1 kg of hydrogen just has about 40 kilowatt hours of energy. So there is a need to compress hydrogen. And when we compress, you have to compress it to very high pressures, ranging from 100,000 bars. At about 700 bar, 1 kg of hydrogen comes down to 20 liters. But to compress it, you need compressors, you need external sources of energy, and that consumes of almost 25% of the levelized cost of hydrogen. I'll just bring what I understand by the levelized cost of hydrogen. It is the cost of manufacturing, storing, and transporting hydrogen to its end point, 1 kg. So currently today, the levelized cost of hydrogen is almost 600 rupees roughly. Some people claim it at 200, but actually it works out close to 600 until technology improves. So there's a need to compress it to much smaller volumes, down to 700 bar, where it is 20 liters. At 1000 bar, it's about 60 liters. Another method of getting it down in size is liquefaction. But as I said, liquefaction is equally challenging because hydrogen liquefies at minus 253 degrees centigrade. And when 1 kg of liquid hydrogen occupies 14 liters, but the liquefaction process is 30% of the LCOH per kg of hydrogen. So these are the challenges. You can either compress it and store it, or store it in gas form, or compress it, cool it, and store it as liquid. Now, if you want to compress it, we need to compress it in two forms. One is static storage, and the second is for transportation. Static storage, you can, so weight is not such an element. It's not so important because it's static storage. So you have different types of static storage, but when you transport it either by truck or by large transporters or by pipeline, there are a different set of challenges. And another very interesting area is which the government has spoken about in its latest policies on underground storage. So you classify the storage as type 1, type 2, type 3, type 4 storage and underground storage. In type 1 storage, the storage container is 100% metal. You normally can store up to 200 bar in such containers, but to put layers of metal, you can reach 1000 bar. It is the heaviest method of storage because of the amount of metal involved, but it is the cheapest. And it is best for static surface tanks. In type 2, you partly use carbon FRP, fiber reinforced plastic, the metal. It's costlier, but enables greater storage and again used in static surface tanks. In type 3, you have metal which is fully lined with carbon FRP. You can store up to 700 bars. It is good for transportation. In fact, many of you would have seen the videos of the Toyota Mira car. It has got 4 tubes on it, which has got type 3 type of storage. Each of them can totally it can carry about 5 kgs of hydrogen on this 5 tubes on it. Each tube is 1 kg. And it gives you almost 600 kilometers of coverage on this with this 5 kg of hydrogen. 4 is much costlier. It is purely plastic lined with carbon reinforcement plastic. You can go in for very high pressure. It's the lightest and costliest, and a lot of research is going on to bring that cost down. Another very interesting method I spoke to you about is underground storage. You have, you have extracted oil and gas, large caves or coal, large caves underground, which can store hydrogen in cubic kilometers, not cubic meters, but cubic kilometers. What needs to be done is to seal the walls of the caves with rock salt solutions. Seal the entrance with the physical methods. And interior walls of the cave to be sealed with rock salt solutions, which form an impervious layer, so it does not allow hydrogen gas to easily escape. And very large scale storage happens. This as an example, there's a place called Teesside in UK, where there's this salt cavern where it can store 70 cubic kilometers of hydrogen at about 25 bar. So lower pressure required, larger volumes. And this just this one salt cavern can store 27 gigawatt hours of storage capacity. That is much more than what India needs in its plans till 2030. But you need to be careful in the filling process of hydrogen into a salt cavern and while emptying it so that it doesn't leak off. Another key challenge in storage is metal reacts with hydrogen to form hydride. And it causes embrittlement of material. And it can cause sudden fracture. So we have to take care and treat the metal for that. And there's a need to prevent leakage. So that is the challenge in hydrogen, storage of hydrogen.
Thank you for that. Yes, challenges of storage are evident from what you said. And that brings me to the aspect of transportation. The transportation of hydrogen from point of production to the point of consumption offers interesting challenges. Could you elucidate on various methods by which hydrogen can be transported? Vijay,
Sure,
please.
sure. First is we got to compress the hydrogen or liquefy the hydrogen and get it into a storage container which is transportable. So for compressing hydrogen, you have mechanical compressors which use up can compress up to 700 bar, 20 to 700 bars. They consume energy, which is almost 15% of LCOH of hydrogen again. Then you have non-mechanical compressors like electrochemical compressors. This is a very interesting field where you use a proton electrode membrane, PEM it's called, which can generate and also compress hydrogen. Then you have metal hydride compressors where low pressure hydrogen is passed through heated metal hydride, pressurized to high pressure, and then it can be put into the storage container. For liquefaction, which I just discussed, you got to first compress it to 80 bar, then you cool it to about minus 140 degrees centigrade using liquid nitrogen. Then cryogenic coolers to cryo cool it to minus 246, further compress it to minus 253 to get liquid hydrogen. And this is a very energy consuming process again. If you have a 50-ton plant per day, 50 tons of hydrogen, you consume an LCOH of almost 30% of the cost of hydrogen. If you have a smaller one of 5 tons per day, then the energy cost is even more. So almost 25% of the energy in hydrogen is used up in liquefaction. And similarly, in case of compression, about 50% of the energy in hydrogen is used up for compression. So we can physically compress it into tubes or into a transporter. It could be liquid, it could be in gas state. Then you can also transport hydrogen through pipelines. So you can create separate pipelines for hydrogen and transport it along that. And immediately you got to recompress it so that the pressure is maintained throughout. Or another method is you blend it. You already have existing ammonia pipelines, you have existing methane pipelines. You can blend it into ammonia, you can blend it into methane and send it across. Or at the starting point, produce hydrogen, have a factory which mixes hydrogen and nitrogen, creates ammonia, you transport the ammonia. At the far end, you crack the ammonia back into hydrogen and use the hydrogen. Same way with methane. So these are the various methods of transporting. So if you look at hydrogen supply chain, one method gas. So gas to compressor to storage tube to trailer to far end, put it in a high pressure static storage, which is the dispensation point. Another method, gas to liquefy to tanker to high pressure static storage at the other end and use it for dispensation. Liquid hydrogen to the transporter and send it across. The very interesting method is today between Japan and Australia, you have Kawasaki, which is large ships which can carry up to 1250 cubic meters of hydrogen and regularly takes hydrogen from Australia, where there's excellent manufacturing of hydrogen, and takes it to Japan for consumption. So you can transport it by ship. Then, of course, as I discussed, you can use ammonia, which is NH3 methanol CH4, to existing pipelines to a cracking unit on the other side and use it as hydrogen. Now, what does a hydrogen pipeline look like? So a pure hydrogen pipeline consists of thick carbon steel, which is treated for embrittlement and leakage. So as a case study, I just wanted to bring out that example. In US, they have set up a 1500 kilometer line of pure hydrogen pipeline. And at every 500 kilometer point, they've got a compressor. It has got a capacity of 4.5 tons per day. and capex cost to construct this was almost $6 billion, and its annual OPEX is something like $200 million. But because you're transporting so much through a pipeline, the cost, levelized cost of hydrogen on this per kg came to about 50 rupees. But it is cheapest to repurpose the existing gas pipelines. You already have an extensive gas pipeline network. If India has to look at it, GAIL has got massive pipelines covering the entire breadth of this country. So if you repurpose this existing pipelines and use it, it further reduces the cost of the hydrogen. How do you repurpose it? You have to put a safety coating to reduce adsorption of hydrogen. You put inhibitors to reduce reaction of hydrogen with metal. Another solution is you insert a pipe in the pipe. A pipe based on plastic, etc., which is light. So that's how you transport hydrogen across the country. Yes. And now, when we look at, finally, it all boils down to cost. This whole mission is how do we get cost down? Everybody knew how hydrogen is produced for the last 100 years. We were taught in school about the process of electrolysis. The challenge is to make it cheaper and usable. It has to become comparable in cost. The levelized cost of hydrogen should be comparable to the levelized cost of normal power. Only then will people switch. So today, if we look at it, water electrolysis, 1 kg of hydrogen needs about 55 units of power. So if we are talking of pure green energy, 1 kg, 55 units of green energy at 5 rupees even per unit, it costs about 250. So the cost of producing hydrogen is costing straight away 250 rupees. Of course, if you have a dedicated green plant, it comes down to half of that. Now, energy required for storage plus the capex costs another 20% of this, with another 50 rupees per kg. If you want to liquefy it, another 20%. The transportation increases the cost by another 20%. So finally, the levelized cost of hydrogen, that is the cost of 1 kg of hydrogen at the point of consumption, comes close to 500 rupees a kg. And with all types of taxes, it comes to close to 600 rupees a kg. So 1 kg of hydrogen has 40 units. So effectively, a unit of power from green hydrogen costs us about 16 rupees a unit, whereas it is 3 to 5 rupees for green energy. A kg of hydrogen today can drive a car about 100 kilometers. So that is 6 rupees a kilometer. So it's comparable to petrol. But when you look at pure electricity-driven cars, it is only 1 rupee a kilometer. So it's 6 times the cost of electric vehicle. But the advantage of hydrogen is its lightness. Batteries is where you can save. Therefore, today, hydrogen is best suited for large haul transportation, like ships, trucks, as battery weight makes it very large. Ships are massively switching over to methane and hydrogen. In fact, I had attended recently the Indo-Danish summit in IIT Madras, where the CEO of Maersk, which is the world's largest shipping company, said they are going to switch rapidly over to methane to hydrogen systems on their ships. It is also very suitable. Comparable to transportation, great sources of pollution in the world today are steel manufacture, concrete manufacture. So if we use green hydrogen there, you can reduce carbon emissions massively. Thank you, sir.
Thank you very much, Brigadier Vijay. Viewers, we have had the privilege of listening to Brigadier YVR Vijay, who is an expert, as you can make out with the depth of his knowledge, the clarity of his thought, and he is telling us how this wonderful roadmap which has been announced will move forward, and the new technology is now happening. And any of the viewers who want to know more about it, you're most welcome to get in touch with Brigadier Vijay. The link to the article, which we referred to at the start, as well as the link to Brigadier Vijay's LinkedIn profile, are there in the show notes below. As I mentioned, you can get in touch with him for further advice, further clarifications. If you like the content of what we are having on our channel, do subscribe to it. We look forward to having you back with us in future episodes. We are a platform for MRO professionals, and we are also focusing on clean energy, green energy, and we have got experts, very good experts on that. And any MRO professional is welcome to join our platform. With that, I once again thank Brigadier YVR Vijay for what he has spoken today. And thanking you all, viewers, we bring this episode to a close. Thank you very much, and Jai Hind.